All right, class, let's take a look at some more AC circuit stuff. So this will be our AC circuit video 2. And essentially what we're going to look at today is a way to represent both the voltage and the current in these AC circuits, and how to find one if you have the other, and then a little bit of what it means to be working with some imaginary terms and numbers. But before we hit the actual AC stuff, I want to just take a second and let's just look at a DC circuit just to kind of remind ourselves. And sorry, that is like the worst drawn resistor in the world. Maybe that's a little bit better. So here's resistor 1, resistor 2, some voltage source V, it's DC. Okay. And there's a lot of stuff I can do with this. Oh, let's ground it, because, oops, that's in the eraser. Let's ground it. Okay, there's a ground. Marvelous. Okay, I can apply Kirchhoff's law here, or I can say, okay, if I start at this corner, I can walk myself around the circuit this way, and I could say, okay, that was my son. I can say V minus IR1 minus IR2 equals 0, right? We've been doing these things. It's something that we understand and we know well. And if I wanted to solve for the current, right, I could, I could move these. I could move these terms over here, and then I could factor the I out and divide the R's over, right? And I could get an expression for the current that essentially looks like this, right? That this is going to be R1 over R, right? And hooray, we have the current. And now there's lots of stuff I can do, okay? So for example, if I wanted to know the voltage at this node here, we could start at 0, and I could go across here and across here, and now I'm there. So, right, I'm looking at this piece of the circuit. So if I take V minus IR, it'll tell me what the voltage is at this node. I have an expression for I, right, and there's all the marvelous things that I can do, and I could go through and solve and just really soak up the DC circuit piece of this. But the thing that I really want to look at is okay, so DC circuits are marvelous, but how does this work in an AC circuit space? So if I draw an AC circuit, so here's plus and minus, and there's my little AC source, and I come over here, and then I'm gonna, let's put an inductor, and let's come over here, and let's put a resistor, and then might as well even include a capacitor, right? We might as well put every single thing in here that we can, right? So inductor is L, resistor, capacitance, voltage source. And the one thing we need to keep track of is that this V, right, is not just some number, right? Now it's an expression that changes over time, right? So we're going to define this as, so the voltage is changing over time, so there's some peak voltage times the sine of omega t, and we can put a plus phi there. The point of this is, and the reason why I'm representing it this way, is that my voltage is it changes over time, right? It's now if I can start this here, and then my voltage is going to fluctuate and change over time, right? It's going to follow some sine wave, where the frequency that this is changing is hiding inside of this, right? Where omega is equal to 2 pi times the frequency, okay? And so typically you're given like the peak voltage. Oh, and by the way, right, if I'm peak voltage is right here, right? There's VP plus, or you can say there's VP minus. And so I have all these terms. And in this case, right, because I started here, okay, this is going to make phi 0. And that's just marvelous and lovely. And we love that. So, so I've got this thing that defines and expresses the voltage. Oh, look at me. Let's ground this beautiful circuit as well. So we've grounded this circuit as well. And so with a ground, I can say, hey, what if I wanted to know what, just like I did before, right? What is the voltage at this node, right? Sitting between the inductor and the resistor. And so then to do that, you might say, I need Kirchhoff's law like I did before. So I'm going to have the voltage minus I times ZL, which is the impedance of the inductor, minus I times ZR, which is the impedance of the resistor, minus I times ZC, which is the impedance of the capacitor, equals 0. Boom, Kirchhoff's law. And then I can say, oh, marvelous, just like I did before, if I'm starting from here and I'm going to jump over this and over this to get to this node, I just need this much of the of this expression to tell me what the voltage is at that node. By the way, we could have snuck the other way, right? Because I can move these two over to the other side, and those are equivalent statements. So either one of those ways will get me what the voltage is at that particular node. But, okay, so then I come here and I say, oh, marvelous. Okay, so I already have an expression for the voltage, and ZC is just, excuse me. Oh, see, this is going to kill me. My L's and C's are just too much alike. That's an L, and that's a C. Curse L's and C's. This ZC is just, it's an expression, it's what? It's J omega L. But the thing is I don't know I. Up here, I was able to get an expression for I right here. So I need to do the same thing in this circuit, okay? So we can say, I can do the same thing. I'm going to take these pieces, and I'm going to move them over here. I'm going to factor the I out and divide the other stuff over. And we can do that, right? And then I then becomes the voltage divided by ZL plus ZR plus ZC. And we say, oh, this is marvelous. This looks pretty easy. I'm done. Except for we're kind of not, right? There's some more stuff going on in here. This V, right now I have it expressed as this sine function, which may or may not be good for the things I'm trying to do. And let's see here. And I need to fill out what the Z's are, right? So I can come in, I can make this, I can take this further. I'm going to leave that as V for right now. ZL, like I said before, this is J omega L. ZR is just R, which is beautiful. And ZC is negative J over omega C. And I have all these things, and I look and say, ooh, I've got some imaginary terms in here and some real terms. What am I going to do? I can pull these things apart. I can separate the real and the imaginary, right? Where we can say, okay, oops, there's the eraser. R, we'll just say plus J times omega L minus 1 over omega C. Okay. And now I've separated this into a real piece and an imaginary piece, right? And this is going to be really important for us in a second, but I'm going to pause where we are right here, and we're going to slide over here. Ooh, well, I'll zoom in over here. I'm going to slide over here, and we're going to think about how to deal with these imaginary bits of this. Okay, so a little bit ago we looked at and said I can think about these voltages and currents in a little diagram here. I can say, okay, there's 0 and there's pi halves, and here's pi and here's 3 pi halves, and I can say, okay, well, what if I stick my voltage right here, and then what if I stick my current right here? And these are just arbitrary. I'm just putting these in arbitrary places. And that's V, and there's some phase angle between them, phi. And we know that over time, right, as time progresses, right, here's 0 and pi halves, and pi and 3 pi halves, right, at some other time, V might be here, and then I is going to be somewhere over here, where the angle between them is still phi, right? That's not going to change. So those things are going to move together in time as they kind of spin around this this clock, and we can plot this, right? We have a plot right here, right? of the voltage. And if I wanted to add, I'm going to make a new one. So here's my plot versus time, and I'm starting the voltage at 0, and so this is going to go something like this. And then I've started the current ahead of it somewhere. So maybe this is what the current is going to be doing. But the point is that the current, there's this shift between the current and you have to pretend that these distances, oh man, they just don't, all of these little red distances are equal, right? And this is related to phi, right? The amount that these things are shifted off of each other in time, okay? And so we've seen this, but I'm going to represent it one other way. There's one other way to kind of plot these is, so here's J, negative J, and I know imaginary numbers are I, but in physics we thought it'd be really funny to make current I, and so sometimes it's capital I and sometimes it's lowercase I. So I can't use little I right now for imaginary because I might confuse that with current, so I'm going to use J, but don't, anyways, we're just going to use J, but this is lowercase j. And then I have 1, and I have negative 1 over here, and I can do the same thing. Look, I can put the voltage right here. Here's my voltage, and I can put the current right here, right? And what this is telling me is that right now, at this moment in time, all of my voltage is real, but not all of my current is real, right? Some of my current is real, this piece, that's real current, but some of my current is imaginary, this piece, okay? And if I add the yellow, the real and imaginary vectors, I get back the current, right? So I have this triangle, and I have these relationships I can build, okay? So I'm going to say, well, let's say the magnitude of this is A, and let's say that this angle is phi. And so I can say, oh, well, so this side is just A. So the real side, right, is A cosine of phi, and the imaginary side is A sine of phi. And if I do that vector addition, right, I can add these together, and I get A cosine of phi plus A sine of phi, and I'm going to just put this little hat, this little imaginary hat here, just saying, look, that's the imaginary piece of this thing that I'm looking at. Okay, but I've built a coordinate for me, and a coordinate, and the important piece here is that this coordinate has a real part and an imaginary part, and I mean you can probably see where we're going with this. Right? I can use Euler's theorem, and I can say, hey. Euler's theorem says this, that if I have that a times e to the jx is equal to a times the cosine of theta, or excuse me, the cosine of x plus, we're just going to use j because that's what we've been using, j times the sine of x, right? And I have this thing where I can go back and forth between these expressions, and this is going to be super useful for me. So I can rewrite this vector, this in Euler's form, right? Where this expression is now a times e to the j phi, okay? And so this is going to be really important, okay? So I have the power to do this, and we are going to be leveraging this. We're going to be building this triangle and thinking about this real and imaginary plane all the time, right? This is going to be hugely important to us, and being able to think about and know, like, where is this angle and why does it matter where it is, okay? So keeping all this in mind, let's slide back over, and now we're looking at this thing, which is in my denominator, and now let's unpause, okay? And we look at this and we go, oh my goodness, look, I have a real piece and I have an imaginary piece. So can I then plot this on the real and imaginary plane, right? So here's my j and my negative j and my 1 and my minus 1. And I can, right? So I'm going to, looking at this, hold up. Do I have all my signs? Let me check and make sure I have all my signs right. Yeah, I'm going to add all this stuff over. These are all positive. And these end up like this. I think I have all the signs right. Hopefully I do. But anyways, so I'm looking at this and I say, ooh, here's R. It's in the real plane. And then I have this thing in the imaginary plane. Now, whether this goes up or down depends on which one of these terms is bigger, okay? Let's pretend that this term dominates, right? My impedance term dominates my capacitor term, so let's pretend that it pushes it up, okay? I can pick values to make it do that. It could have gone down, but for right now, let's just have it go up, okay? So here are my pieces, right? And this is going to be omega L minus 1 over omega C, right? That's the magnitude of that piece. And so the resultant vector here, let's call it A for fun, it has some offset angle phi, okay? So now I'm staring at this thing. And this is kind of the important piece of all of this, because now I can rewrite, I have this pretty messy expression that I can now use this relationship, right? I look at this and I say, oh, this is just a coordinate, this coordinate, on the real imaginary plane. And if I build it out and I use a little bit of trigonometry in here, I can rewrite this in Euler's form like this, A e to the j phi. Okay, this is so much happier to work with than what I had before. Okay, so now, scroll down some more. So now my current looks like this. It's this V expression over A e to the j phi, where A is equal to the square root of R squared plus omega L minus 1 over omega C quantity squared, and phi is equal to the arc tangent of omega L minus 1 over omega C over R. Okay? And we have this, and we're getting pretty close to being done. Let's come back up here and I can look at this, and I can realize that I can also rewrite V in Euler form, right? I can say, oh, you know what? Like here, at this point in time, I can change this to VP e to the I or to the j, sorry, the imaginary piece, omega t. And that's the peak voltage with zero phase shift, right? Because I've started it here, so zero phase shifting at time zero. And if you look, right, it is the sine part, so at this point it's all imaginary, which is, so there's some happiness going on. But anyways, I can come back here, and now my current is so the current is equal to the peak voltage times e to the j omega t over a e to the j phi. A little bit of algebra later, and I have Vp over a times e to the j times omega t minus phi. And so here's the expression of my current. And by the way, guess what this is? That's IP, right? That's the peak current. Boom! Got the peak current. I know how much the current is phase shifted off of the voltage, right? This tells me right here. And I'm ready to go, right? This is so much easier to work with. And that's the beauty of using, and that's the reason why we're using these imaginary numbers. It's so much easier to work with that than these long sine and cosine expressions, which we could, right? We could live in that space, but why if we don't need to? Okay, I've got my expression for my current, and so So then back to that original problem where we started, right? If I want to know what the voltage is at this node, well, it's just going to be V minus I times ZL. Well, now I know what I is. I have an expression, right? Here's the expression for VP. I have the expression for I. I know all the things in ZL, and I can figure out exactly what the voltage is at that node. And it's going to have its own peak, and it's going to have its own phase, right? That's going to be shifted off of the phase of the battery and the current, right? And I can solve it, right? And honestly, probably the easiest thing to do at this point would be to feed this thing to Mathematica or Wolfram Alpha, and I did that. So let's take a look. Well, okay, I didn't. Okay, that was a lie. I didn't do that. I fed this into Wolfram Alpha, right? So that we can see this relationship. So let me go back. Let me show you that. I actually need to change one thing up here in the original. This needs to be positive. Go. Okay, and so, and I don't have a laser pointer here, so you can't, but you can see my imaginary real plane plot. There's the vector on the imaginary real plane. Here's these values. So in here, this is A, and that's phi. So if I come back, so A here is 10.472. So if I were to come back here, I know right now that A, this thing is going to come out to be 10.472, and I could stick that here underneath whatever the peak voltage is to get the peak current. And I have phi, so I know exactly how much the current is shifted off of the voltage. And yeah, so that's a walkthrough of how to kind of think about and do some of these circuits. Honestly, getting good at this just takes a bunch of practice. It takes some time working through the different scenarios. It can be helpful to take some time and plug things into Wolfram Alpha, right? I've got this expression here, and you can see the input line here, and I like to look at the input line because then I can double check to make sure I entered everything correctly. And then looking at the result is important, right? So I've got the 10 plus this thing. So that 10, I look at that and say, oh, that's my real piece, plus the 3.1097, that's the imaginary piece, right? Those are those vectors that make up this triangle down here on this imaginary real plane. But the nice thing is, oh, look, I mouse over, I'm not mousing, but you can see there's the Euler expression that has the magnitude of that vector and the phase angle of it. Okay, so I mean, I like Wolfram Alpha for that. I think Mathematica has similar features, but anyways, if you have any questions, send them to myself or to the TAs. And practice this. Right? Make up some circuits, run through the math, do some practice, and I'll post some more videos where we look at circuits that have some branching loops that get a little bit trickier in terms of what we can do. And most of the time with the ones with the branching craziness, we may not spend a lot of time here, going into these spaces just because we'd have systems of equations, but anytime there's only one loop, like you can do this and work out the current really easily because it doesn't branch. But anyways, I hope you have a marvelous day, and I will see you later.